right, so we've already done a wee bit of review over this. We've talked about cells. They can live alone, they can live with each other, they can become more and more complex organisms. We have our prokaryotes, meaning before a nucleus. Now these prokaryotes, it's not to say they don't contain DNA, they do, all cells do. It's that their DNA is not contained within a nucleus. Reminiscent, we discussed of our mitochondria. Eukaryotes means nucleus. So now we have a much more complex DNA, and it is going to be found in the nucleus, which we started comparing to like the castle, and the DNA is the king who's yelling out instructions to his minions, much like myself yelling out instructions to you. There's our picture. We talked about why cells have to be small. Well, if they were too big, we wouldn't have the brain power to govern and rule them, and we wouldn't be able to provide them with the energy needed to sustain them. Now, that's not to say we don't have some relatively large cells in our bodies. Muscle cells are pretty big. Nerve cells are pretty big. But for the most part, in comparison to like your overall structure, pretty small. These larger cells, though, do need to be multinucleated. We need to have brains to govern. We need to have instruction manuals to govern certain sections of that cell. The cell membrane, also known as the plasma membrane, that means the same thing. That is the skin of the cell. It separates the environment from the inside. We had our jelly-like structure, the cytoplasm, which is what keeps the cell kind of inflated, keeps it pliable, but also allows our organelles to kind of have something to float around in. I think last week I compared it to the stapler in the Jell-O. For those of you that are office, you all know I'm an office fanatic. I don't even know how many of you even know the show. I'm assuming you all know the show I'm referring to. Anyone else here a super fan? You're gonna love this. Oh, sweetheart. You need to go right now. Excuse yourself from class and go start watching it right now. Right? Michael? The nucleus, as we know, contains all of the genetic material, and the genetic material is just the blueprint, the how-to. What do we need to do? How do we need to do it? Here is our cross-section of the cell. We're going to talk about all of these little blips in here in the part 2 section, but all of these are the organelles, or medical terminology quite literally translates into tiny organs. Inside our cell, we have some organs that function like your lungs, cellular respiration. We have some that function like your kidneys to detoxify things. We have some that function like your liver to repackage and convert things into other stuff we can use. We have other structures that are just little factories, and their whole job is just to build stuff, kind of like your small intestines, and also like your liver. We have some cells like a lysosome whose only job is to destroy stuff, and eventually he will, in fact, be programmed to be a little time bomb and destroy the cell itself, because cells are not immortal. They don't live forever. But how do they know when to go? How does your body know when to die? Lysosomes.
So is that part of the white blood cell that after the white blood cell attacks the foreign body, it destroys itself? Or
So the lysosome, the lysosome is the name for the structure itself. However, the lysosome does contain almost like a digestive enzyme. And so in the healthy lysosome, what will happen is we'll have a little foreign invader, and we'll have and it will trap it, and then the lysosome will come up and kind of join and open and flood it with the digestive enzyme, destroying hopefully the foreign invader. And then of course our immune system has its own form of this, which would be how we get rid of dead and dying full cells. Like in our monocytes, they have little vacuoles that are filled with this enzyme that will digest it. But eventually, as this cell ages, it'll develop more and more and more and more and more of these lysosomes until finally the countdown is complete and they all just open up and flood the inside of the cell with digestive enzymes, terminating the whole cell. It's actually, we kind of call it the suicide because it causes the cell to self-die. So we talked all about our cell membrane, capable of self-repair, very similar to your skin. Separates your insides from your outsides. It governs what can come in and out of your body. We talked about the structure, how it is a phospholipid bilayer. Yeah, we have a hydrophilic, hydrophobic. We have the heads which face out and the tails which face in, which the head or the tail is hydrophilic. The heads, remember the bison? And the heads face outward because they love a fight. And the tails are hydrophobic. Now, the reason, kind of the whole reasoning behind this is if you can see here, in this particular structure, here we have the heads, hydrophilic, here's the heads. So we have a very narrow, very small layer of stuff that loves water. In comparison, we have much, much wider area that repels water. And that is by design because we don't want to just gain and lose water willy-nilly. Water is the most important resource your body has. And so we have to be very regulative with it. And so this is so water cannot easily pass back and forth through. In fact, it takes an awful lot of effort to get water to pass through this fat layer because water and fat don't mix, do they? No, if you've ever tried to clean a chicken pan, you remember. We had all sorts of things that are embedded in our cell membrane. We talked about our proteins. We had our integral proteins. These are any proteins that occur within the bilayer. Integral. And integral just means they are kind of embedded. They are part of the primary structure. We also had our channels. We had selective versus our pores. And we compared this to going to a concert at Cindy Woods. Right? If you're going to go to the concert, we're all going to go now to a concert. We all have a ticket. You still have to have a ticket to get in, okay? If the cell is the concert venue, you still have to have a ticket, but we have a couple of different entrances. You have your selective, which is the VIP. Only certain molecules, only certain ones of us are going to get through and go to the VIP. I am going to VIP. Saying if you've never done VIP, it's worth it. And then you have your pores general admission. Still need a ticket, but it's much less selective as far as who is allowed to come into that entrance. And the pores, that is where we're going to have our water moving back and forth because it's just like a little turnstile. A little opening in that lipid bilayer, making it easier for the water to pass. Again, they still have to have the ticket, but they can pass.
I've got a question.
Yes.
Isn't it where they enter, they also have to exit?
I did not get that. Charles, I didn't get what you were saying there.
have to exit the same entrance, right?
Yes, they have to exit the same entrance. Now, obviously, am I simplifying this to a billionth degree? Of course I am. For what we need, if they've entered a pore, they have to exit the pore. If they've entered the selected, they have to exit the selected. VIP can only enter and exit through VIP. General admission can only exit and enter through general admission. Here we just had our picture. Here's our proteins.
Water can only go through pores.
Yeah, we have to have a very special door for the water because of the width of the fat layer, the hydrophobic layer. And so water has to have a very special opening in order to bypass that fat layer. We had our peripheral proteins, peripheral meaning out to the sides. And these peripheral proteins, not so much involved in the movement of molecules back and forth, but rather with the shape manipulation of the cell itself. Because cells are constantly moving and changing shape based on what they need to do. And so we need the cell to be able to change its shape, get super flat, get super round, depending. And it's the peripheral proteins that help it do this, but not allow it to damage its cell membrane while it's kind of manipulating and moving and flexing and ebbing and flowing. Think of specifically your muscle contractions. Muscles are some of the most noticeable shape and size changing cells. Just if you look at your bicep from your elbow, because your bicep actually joins down here, and joins up here, and when you flex, it shortens by over half and gets very thick. That's what brings out the guns. Welcome to the gun show. That's mainly because of these peripheral proteins. All right, this is where we left off last week. How do cells recognize each other? Very similar to me looking out with my eyeballs and seeing you and recognizing you based on your cell membrane, your skin, your features. Cells also have features that they use to recognize each other. Now, this is not obviously, do our cells have eyeballs and a brain to interpret visual data? No, of course not. What they do have is a specialized sugar on the outside of the cell. It's this very sticky type sugar called the glycocalyx. Glyco meaning sugar. Calyx just means to surround. So the glycocalyx. And these are going to be unique. And this is how I can determine, are you supposed to be here or are you stranger danger? Because cells are constantly coming in physical contact with each other. Constantly. And so when I come up and I'm like, oh, here's my cell. And I'm like rolling past him and I'm like, oh, okay, you're supposed to be here. Hi, have a great day. See ya. Bye. Or I can roll past and identify stranger danger and start making messages to my immune system. So even my cells, my viruses, bacteria, parasites, this glycocalyx is how my little private investigators, my antibodies, are able to determine stranger danger. They have a printout of the glycocalyx and are able to determine, yeah, this is the guy we're looking for. And so that's how our cells recognize each other. What's really kind of interesting is when you get into this glycocalyx, some of these, especially parasites, I find parasites really fascinating. Very fascinating. You won't get into that until next term with Ms. Nelson in Lab Pro. Parasites are amazing. Okay, not if you have them, but just to learn about them. Some of them, as well as some bacteria, as well as some viruses, they know. They're smart. And they know that your body is going to try and destroy them. Well, do I want to be destroyed? Of course not. So what they can do is they can hide inside. They burrow into other cells. And then your body is now, so let's say I have a little virus. And this little virus is here's my virus. And it's going to come down, and now I have this virus or this parasite is now very happily living inside this cell. So now when I am an antibody looking for stranger danger and I pass over this cell, who do I detect? This is the cell. And he's in there like, just hiding, and my immune system does not recognize, and he is now proliferating, and he's reproducing and proliferating, and in some viruses it's pretty terrifying because he'll just go in with his shenanigan pants, and he'll just be like, look at all this lovely DNA. Sure would be a shame if someone messed it up. And he just starts doing that. He just like, oh, let's take this little protein and set it over here. And let's take this little protein and set it over here. And he starts changing the DNA. Well, when that DNA replicates through through mitosis, don't we get an exact replication of DNA through mitosis? Do I correct it? No, I just start replicating. Well, what he's actually doing, and this is why viruses and some parasites are so terrifying, because what he's doing is there are parts of that DNA that is, hey, I'm going to recognize you and I'm going to kill you. And this little virus, we're going to call it the Huff virus. I'm now the Huff virus, and I find this little code that says, find Huff, kill Huff. And I'm like, oh, that's rude. Rude. And so I'm just like, okay, now guess what it says? Love Huff, give her everything. And that's what begins to get replicated. And so now you have this love Huff, give her everything message instead of find Huff, kill Huff. And that's the message that's now being replicated into new cells. Okay, I thought you guys would be a little more enthused about that. But no, I'm enthused enough for all of us. That's all that matters.
The movie Osmosis Jones is really got to find that. I mean, it is a good show, but his movie, but.
What is it?
Osmosis Jones.
I have not yet seen that movie. I've been told multiple times to get off my Huff butt and watch it, and I just have not. So I will have to do that because I've heard Osmosis Jones is just fabulous at explaining all of this. But I find that fascinating. Radiation does the same thing, except radiation just goes in and scrambles everything. It just basically just alters everything.
And then does mitosis, does it copy the scrambled DNA?
Yes!
Oh, okay.
That's what I'm saying. So I have now either a virus or radiation, something goes in and scrambles up the message of DNA. Because the whole point of DNA, again, simplifying to the millionth degree, of course I am. But what DNA does is the blueprint for everything that cell needs to know about everything about you. And so as a virus, as radiation, I go in, I scramble it up. Well, now through mitosis, I'm making an exact copy of that DNA. Except now I'm making the wrong DNA. It would be no different than you have taken your notes. You are a cell. Your notes in this class are DNA. And somebody steals your notes and rewrites them with all the wrong answers and sneaks them back to you. And then you're like, hey guys, I made a great review for the next test. I'm going to copy off copies for everybody. and you go with the incorrect copy that someone has now snuck you to the copy maker, and now is it changing it back to what you had? No. And then you hand this incorrect copy to everybody. They all use it to study, and then what happens when you all take the test?
No.
We all fail. And then guess what? They start looking at you and they're like, hey, immune system, we got a bit of a problem down here. And the problem is, though, is that nobody knows it was you that made the copy. All they know is that you guys got an incorrect review. So what do? We start turning on each other. Well, you're the one that gave me that copy. Well, I got it from her. Well, I got it from him. Let's trace this back. And suddenly now your whole cohort is just fighting, punching each other in the throat, keying each other cars in the parking lot. But the problem is that the more that happens, the more replication, more anger we get. Suddenly now we got a bunch of rogue cells who are not doing their job. If, let's say, you guys are all liver cells and your job is to make my liver healthy, and you are too busy fighting amongst yourselves and your DNA is mixed up and you are no longer working as a unit of liver cells, guess what's not working? My liver. So then I'm in liver failure. And now I've got to do some sort of Control-Alt-Delete reset where I just wipe all of you out and hopefully get healthy cells replicating once again.
And that's what they're hoping to happen with chemotherapy.
That's exactly what they're hoping to happen with chemotherapy. Some chemos are selective, where it will only kill off the rubies. Right, so let's say again, VTI is the organism. We have 4 different groups of organ cells. Some chemotherapy will only wipe out the rubies. And a few of you, hopefully healthy cells are going to survive, and you are the ones that will then replicate and repopulate the ruby cohort. Other chemotherapies are going to wipe out the entire school population. And then hopefully the very few strong, healthy cells that remain. Or I can get a donation and introduce new healthy cells that will then replicate with the appropriate DNA. Right?
Yeah.
Come on. How are you guys not more excited about this? I don't understand you. It's like I don't even know you. It's never too early to get excited about anatomy.
Oh, it's very interesting.
Because we can apply it to concepts that you're already at least a little bit familiar with. Everyone's heard of chemotherapy. Now, chemotherapy, another just little fun fact, we've all heard of cancer chemotherapy, but there are a lot of other forms of chemotherapy, which is just a chemical remedy that kills off certain cells. In fact, there are oral chemotherapies that are targeting and killing off certain cells. And then of course your injectable for like cancer. But you don't have to have cancer in order to have chemo. Just a little fun fact. Anything that does a Control-Alt-Delete and wipes out a population in order for you to start repopulating, that's chemotherapy.
Okay.
So let me give you a personal example. So back several years ago, I guess, wow, it's many years ago now, it's almost 9 years. Back in like 2011, I got West Nile virus.
Oh, no.
Yeah, I got West Nile. And you guys are gonna learn something about me, is that if there's something bizarre and weird, I'm gonna be the one to get it. So most 99.9% of the people who got West Nile, you probably didn't even know you had it. You feel a little blah for a couple of days, maybe a low-grade fever, you just feel off, nothing to even make you go to the doctor. I got chronic West Nile virus, meaning that it started taking up residence in the cells of my kidneys. and did just that. It started altering my DNA so that more and more of these replicated virus cells could come in and have Rumspringa in my kidneys. But the other problem is that now my antibodies, right, because I have the guys who are looking now for West Nile virus, they now have this super blurry picture and they're not really sure who to attack. So my antibodies just start telling my immune system to just go ahead and attack everybody. Just we're not sure who is the bad guy, just take them all out.
So it becomes like an autoimmune.
That's exactly how it manifested. My immune system mistook my joints and my bones for virus. And my immune system started attacking my kidneys and started attacking all and breaking down all of my joints. So that was super fun. I was completely disabled for nearly 2 years. I had to walk with two canes, and they had to put me on a multitude of oral chemotherapies to reprogram my immune system and get it to stop attacking my joints. And it acted just like, although it was pills, but it was awful. It was dreadful.
Do you now have like a weakened immune system, or is it just a?
So my immune system now is back healthy, but I spent several years where I did have a compromised immune system. And I do have residual, very severe osteoarthritis because of the permanent anatomy changes that it made in my joints. My immune system was basically going into my joints with a buzzsaw and just destroying everything. And so I do still have pretty significant osteoarthritis. I'm functional. I'm painful every day, but I'm at least functional now. Also caused major nerve damage in my face, in the left half of my face. So I have Bell's palsy in the left half of my face. Just super fun. So yeah, glycocalyx. That's a sad commentary on when things go terribly wrong. Terribly, terribly wrong. We have cell adhesion molecules, and what these are, exactly what they sound like. Adhesion means to stick. So parts of the glycocalyx are going to be aiding in bonding cells together, right? If I am off to fight a battle, I want to be arm in arm with my military brethren. I want to know who's on either side, kind of like marching in formation. But the other thing that these cell adhesion stick together, they're also going to help cells move over and past each other. Because if you think about it, a lot of these cells are moving in relatively tiny, itty-bitty little areas. It would be like you and me on a tightrope. And I'm a cell, and you're coming on the tightrope, and I'm and you're coming in the opposite direction, and you need to get that way, and I need to get this way. Well, how are we going to do it? What we're going to do is we're going to stick together. And suddenly now we're on our way. So it helps cells to move past each other. The receptors are for our cell recognition. That is the little wanted poster we talked about. And that's going to help our immune system hopefully find bacteria and viruses, unless of course you're one of the unlucky ones and they take up shop in one of your organs and decide that they're going to hide. Hepatitis is another virus you've probably heard of. Hepatitis lives where? Hepat. In your liver. And this is a virus that hides from your immune system by moving into your liver. And it starts replicating inside your liver cells and doing the mix-up. Hey, don't find me, don't hurt me. Well, the problem is now your liver cells are not acting as liver cells. You start getting liver damage, and unfortunately, you cannot live without a liver. You have to have a liver.
So the two types of membrane receptors, is a ligand a type of membrane receptor?
So a ligand is how are we signaling? That is the type of the type of cell phone. Sorry. Okay. So some of you have Verizon, some of you have AT&T, some of you have Sprint. The ligand is simply what kind of receptor, what kind of communication are you, your personal cell, using? My ligand is an iPhone with AT&T. Your personal communicator might be a Galaxy with Verizon. Now, can I communicate to you through mine to yours? Yes. But in the cell world, it's a heck of a lot easier for you to communicate with somebody who has the same make and model of phone that you do. So ligand is simply how are we sending the messages? These are specific sites on the cell that are bringing about the change, either changing the cell shape, putting the cell on red alert, or telling the cell to stand down. Ligand is just simply what are we using to send the message. Does that make sense to everybody? Does that make sense?
So one of the questions in the test yourself is how does obesity affect cell membrane receptors for insulin?
How does it what?
So what test yourself through two. It asks what are membrane receptors and ligands? What role do they play in the health of the cell? How does obesity affect cell membrane receptors for insulin? I didn't know how to answer that.
Oh, sure.
Wow.
So yeah, that's a little more in depth than that we went into here. So obesity is a huge problem, obviously. What insulin does, first we must discuss what is insulin. Insulin is something that gets glucose out of your blood and into your tissue. All of your cells are very, very greedy. Everyone to get paid. Just like you. If you go to work and they're like, hey, work your regular shift, but we're not paying you for this, bye. Everyone to get paid. And every cell in your body, the currency that you are getting paid is called glucose. So through a whole series of events that we won't get into, you eat the chicken Chipotle, bippity boppity boo, we convert it all into glucose. The glucose gets sent into your blood, and then we have insulin that gets it out of the blood and into your little cellular hand to get paid. The problem with obesity is it affects the gland that creates the insulin. Your pancreas gets fat. And your pancreas is now either under creating the insulin, or it's not creating enough, because your pancreas is programmed to produce enough insulin to get enough glucose out of your blood to feed you right now. So my pancreas knows I need to make enough insulin to pay this size of a body. But what happens if in a year I put on 300 pounds? Does my pancreas know how to sustain that much more tissue? No. That's how obesity plays a role. It's not so much the cellular composition of the pancreas is changing. It's just that the pancreas is pre-programmed with its instruction manual to produce this much insulin. Now, if I have a pet who is obese, my pancreas does not have that instruction manual. And that's where we might see obesity onset diabetes, and why diabetes mellitus much more common. In fact, we say it's the 3 Fs: fat, female, and, well, in human terms, it's 40 fat and female. In our canines, it's elderly, fat, and female are more likely to get obesity related, because our DNA just simply doesn't understand how to make that much more insulin. Does that make sense?
That does, yeah.
Yeah, we're going to talk all about obesity when we get into nutrition, because unfortunately about 80% of our companion animals clinically obese, mine included. Hi, I'm a pet owner and my animals are overweight. Not by a lot, but by a little bit. Let me minimize you guys so that we can see this. So this is just another term, calveolae. Move this down here. Calveolae. These are just little caves. So whenever we are moving stuff in and out of our cell membrane, we don't want to rip the cell membrane. We don't want to rip it. So here's my cell membrane. So what I'm going to do is I am going to, let's say I have this stuff right here that I need to move into the cell. And it's going to come and it's going to join with very special receptors saying, hey, here's my ticket, come, let me come in. But maybe these are much larger molecules. We don't want to rip the cell membrane. So what happens is the cell membrane creates this little calveolae, little cave, pulls it in without destroying or damaging the cell membrane. It's really pretty ingenious. So just specialized areas, maybe we have carbohydrates or maybe we have different proteins that we need to pull in for whatever reason or get rid of for whatever reason. And so these calveolae, little caves, are just little creations of our cell membrane that allow bigger things to pass back and forth without damaging the cell membrane. This is a pretty great picture. I like that picture. Comments, questions, concerns? I'll give you guys a minute. You're furiously writing. Hey, where are you in MedTerm right now? Ooh, body fluids. Fun. Mucus. Have you learned the VTI rules yet? I have 3 primary rules while you're writing, because I don't like awkward silence. Rule number 1 for all technicians ever on the planet is don't eat poo. Seems pretty self-explanatory. It actually is much more complicated. Don't eat feces. What it does is reminds you wash your hands in between patients, wash your hands after every patient. Because let's say you're in private practice, you have 4 exam rooms going, your surgeon's screaming at you because you haven't even started pre-surgicals yet, and he's got a full surgery schedule. 2 of your other technicians have called in sick, and you have a lobby full of walk-ins. You've gone to this room, it's a puppy. So you're doing your typical puppy stuff, you get your fecal, you get your temperature, you start your fecal. As you're passing to go to the next room, you stop by the table, you grab your sandwich, you take a quick bite of your sandwich. What did you just do? You just ate poo. And there's a whole lot of stuff you can get from animals by eating poo. So that's why rule number 1 is don't eat poo. Rule number 2 is don't panic. It's just a little in your back of your mind. There are going to be times when your brain is going to go, oh my God. No, don't panic. Close your eyes, take 1 deep breath. Get your tech tunnel vision and you'll get it through. Body fluids is where we come into rule number 3. You as technicians will never, ever, ever in the history of never, ever write the word pussy in a medical file. It is purulent discharge. Can I say that something is pus, has pus? Sure. Although medically I would prefer to say pyogenic. Pyo meaning pus, genic formation or creation of. I can say the word pus, but I never, ever, ever want to write the word pussy. A wound is never pussy. Because if you are looking at me like I don't understand, Ms. Huff, what is your objection to the, I guess, would it be a Pussy is not really a verb. It's an adverb. We will never, ever, ever write the word pussy in a legal medical document. Just saying. So there's your little med term.
Miss Huff,
Yes.
could you go back? I'm trying to fill off the bus.
With this slide, okay, so caveolae just means literally little caves. And so what I've got is I might have some very large, you can see just how large these molecules are. You can see just how large these molecules, if I tried to move these molecules into the cell, it would rupture the membrane and destroy the cell. So I need to have another way. And so these come in and they have very special receptors. And they say, okay, we need you to open the magic big door. And what happens is the phospholipid bilayer begins to form this little cave and encapsulate these large molecules and then brings them into the cell and will then transport them where they need to go. And then it'll open this up and release them where they need to be. So what we're talking about here with these little caves is just another transport. Instead of using my selective or my pores or utilizing proteins to manipulate the shape, what I'm doing now is I'm just simply using my existing lipid bilayer, because I can see here I'm pulling it in. Here I have extended my lipid bilayer, and then what I'm going to do is I'm going to attach these two ends here, seal it off, and then move this encapsulated molecules into the cell.
So what are some examples of those extracellular materials? Is that what low density lipoprotein?
Yeah, so low density lipoprotein would be an example of something that would have to move in and out via this method. Some cholesterols are very, very large. Some sugars, very, very large. Anything that is so large that it would literally just split the cell membrane in two, and now he's just gonna die.
Well, Ms. Huff, is it kind of like pores where like they open and they close?
It's not really like a pore, because we already have something called a pore, which allows free, pretty much access movement. This is more like a cyst, if you want to compare it with something anatomical. So now this is a very loose analogy, a very loose comparative. You have so what I'm using as a comparative is something we don't want to have come into the body, but it does the same kind of thing. Here I have my skin. Here I have bacteria and debris. And what happens is that bacteria and debris begins to enter. And then finally, I will go, uh-oh, we don't want that. And I'm going to encapsulate it to contain it. That's kind of what's happening, except this is stuff we want to come into the cell. Here, these are all things, and they come, this is my cell membrane here. And these guys come in and they're like, hey, we're super big, but we were told by the king that we need to come in. And if you allow them through this, it's just going to rupture and the whole cell will die. So what happens is, here's my cell membrane, is it's going to start.
Could you repeat what you said? You froze.
So this is my cell membrane, and these are very large molecules. And if I allowed them all to come in, I'm going to split the cell, and the cell will die. And I don't want to have that happen. So what happens is my phospholipid bilayer, I can start adding to it, making this little pouch, making this little what? This little cave. And then what I'm going to do is I'm just going to pinch it off here. So I've pinched it off. And this is now a solid cell membrane. There's no damage to it at all. And this is now free to enter the cell and be transported. And then what will happen is this will release and my molecules can exit on the inside of the cell and do whatever it is they need to do.
It'll open up the same way it did on these that did out there.
Yeah, it's going to do the same thing. These little caveolae tend to be more to move stuff in. And then we have another very similar transport system. It's not called the same thing to move stuff out. But it's exact same manner, just in opposite. Where if I have something I need to move out, I have a transport. It binds with the membrane and releases it so that it can get out of the cell. Extracellular stuff on the outside moving to the inside, that's what the caveolae are doing. So this is just showing one of the examples of stuff extracellular moving into the cell are low density lipoproteins, fats combined with a protein, which are very, very large. And I'm not going to test you over this arterial change with our lipoprotein, but just know this is one of the things that we're going to move from the outside to the inside of the cell. Now, some of our cells, a lot of our cells are static, meaning they don't really go anywhere. They don't leave their little hometown. You don't want liver cells migrating out of the liver. Kind of need to stay in the liver. We do have other cells called wandering cells that use your circulatory system, like your red blood cells, your platelets, your white blood cells. But then we also have some cells that have their own mobility. They're not dependent on the flow of your blood to move. And they have these specialized areas to help them move. Cilia, which is like these little hair-like structures like a sea anemone. You can see a sea anemone moving in the waves. Think more of a crowd surf, right? If I tell you all to come up here and put your hands up, and I do a stage dive, and you're now moving me, that's cilia. Flagella is a physical tail, a propulsion. So some examples would be a cilia. You have cilia in your trachea. When you are breathing, we don't want things like viruses and pollen and bacteria and water droplets from other people getting down, and so it's a little bit more of a protection. You have this very, very sticky mucus in your trachea, and all these big molecules get stuck. And then the cilia crowd surfs them back up. And that's when you get the little tickle, tickle, tickle. And then what do? And then you swallow it. And it hopefully will dissolve in your GI tract. That's cilia. Flagella, the primary cell in mammals would be sperm. Uses this propulsion flagella.
Doesn't amoebas have that as well? Or
Oh yeah, there's a lot of like protozoal parasites. Like there's one that is the happiest of all the parasites called Giardia that literally has a little happy face on him. He has propulsion. You have little other protozoals that have propulsion. You have some that are multi-flagellated, meaning that they have more than one tail. I'm just talking anatomically in mammals, the only one we have is sperm. We have a whole lot of other cells that are ciliated. The one I just gave in the trachea down into the lungs. You ladies out there have cilia in your fallopian tubes. So when an egg comes out of the ovary, it is very gently crowd surfed into the uterus where it is now implanted in the happy little nest that has been created by hormones. Very, very gently crowd surfed. Give you guys a minute. Here, move this. And I'm just going to ask that you know the very generals, that the primary function, cilia is crowd surfing, flagella is forward propulsion. I'm not going to go into the 9 pairs of microtubules and all of that. Now, we are going to talk about that cytoskeleton component coming up. But for right now, I just need you to know the difference between the cilia and the flagella. So, cilia, flagella. Any other comments about that? What's a medical term for blood? Hemo, give me another one. Those of you that are writing notes, don't worry, you're not missing anything. It's just some of you are not. I don't like awkward silences because it gives you a chance to sit and stare at me in a creepy way. Cyto would be specific for cell.
Yeah.
You have hemo, hemato. So hemo, yeah. You're thinking of hemi. Hemi would be half.
Yeah.
Which one's more common, cilia or flagella?
So in an anatomic cilia, far, because mammals only have one type of cell, and it's not even a type of cell that you have. So half of the mammalian population has no flagellated cells.
Okay.
Only half of the mammalian population has cells with a flagella. So far more common because everybody has cilia in the trachea. Everybody, well, all ladies have cilia in their reproductive.
You kind of like glitched for like a second, like whenever you were saying that last sentence. Could you repeat it? Like I think it was basically you just saying that there's cilia in the fallopian tubes, but I don't know if there was like something else.
What I was saying is that the question was, is cilia or flagella more common? And cilia is going to be more common because every mammal on the planet has ciliated cells, but only half of the mammalian population has flagellated cells. Obviously, those of you that have sperm are the only mammals that have cells with a flagella. Now, are there other things that have flagella that are not anatomical normal structures? Of course there are. Like I said, protozoal parasite like a Giardia. There are other types of protozoal parasites that use this to move through the environment. But if you're talking just plain Jane anatomy, cilia, all the way 100%. Oh, my cilia are crowd surfing something right now. Ooh, excuse me. So here's just a picture. Here's a great picture of the cilia. Crowd surf. And then we have these specialized cells that we'll talk about in greater detail. They're called goblet cells. These are the cells that produce mucus. That's their whole job, is to produce mucus. So when here's kind of an interesting, just kind of a related too. So when you breathe in a pathogen by definition is something that makes you feel sick. COVID is a pathogen. Here's what happens. It's not COVID. It's not the virus that will kill you. It's your body's reaction to the virus that will kill you. So you breathe it in and your immune system goes, stranger danger. And so now this little virus is inside your lungs going, hey, this place is pretty great. Pretty great. This is a great place to start a family. Start having a ton of little kids. I'm going to pick out a nice plot of land. Well, your body is like, oh my God. And it signals to these little goblet cells, produce a crap ton of mucus. And the goblet cells just start going, making all of this mucus. So now these little viruses are like splooshed with mucus and they're all like, and they're just stuck. And then the cilia can crowd surf them out. You cough them up and get rid of it, hopefully. But the problem is with some of these viruses is your body might overreact and just starts producing mucus to the point where you're drowning in your own body fluids. Because this mucus is now filling up all the air spaces in your lungs. And if you don't have any air spaces in your lungs, you can't convert air and carbon dioxide, which means your body is not oxygenating, which means you die. It's just your overreaction to these little mucus goblet cells that are now overproducing mucus.
Same thing happens with allergies as well, or no?
Yep, you got goblet cells in your sinuses. And so when you breathe in the pine pollen, your body already has, incorrectly, but oh my God, this thing is going to kill us. It's pine pollen.
Yeah.
Not going to kill you. But start saying mucus, mucus, mucus. And then it has an immune response, which we'll talk about. There's a whole other thing. But that's why you get the pressure and the snot and the postnasal drip. You get the frontal headache because you have two big sinuses right here that will fill up with fluid. And all of your tissue swells up. You might even run a low-grade fever. Because unfortunately, well, fortunately and unfortunately, a lot of these bacteria and viruses have to have a very specific temperature in order to reproduce. And your body goes, cook them all, turn on the heat, and turns your temperature up, which is supposed to make an unfavorable environment for these guys to replicate. Hence you getting a fever.
Yeah.
Yeah, we got goblet cells all over the place.
Yeah.
And I'm gonna leave you with this mental image. Have any of you heard of a show? It was on HBO a while back called, you may not have heard of it. It wasn't very well known. It was called Game of Thrones. Some of you have heard of this. Okay, good. So I think they were all drinking out of these very ornate wine glasses. They weren't really wine glasses. What were they? They were these very beautiful golden goblets. And so now I'm going to be Cersei. If you don't know who she is, she was one of my favorite characters. You love to hate her. She was fabulous. But instead of wine, okay, you remember I'm the queen, and I now have everyone see the golden goblet. Very ornate, very large, very heavy. Except now it's filled with snot. And it's got just mucus. The really good chewy kind. You know, the kind where you cough it up and you play with it like gum in your mouth a little bit. And I now have this whole goblet filled with snot and mucus. Okay, are you ever gonna forget what a goblet cell is? It's so gross. I know. Me very slurpily drinking mucus out of this goblet.
It's like drinking that thick water.
Yeah, it's like drinking a snot milkshake. Yeah, the good chewy kind. The good chewy kind. There's a picture of our flagella. As I said, it's the only mammalian cell is our sperm. There are other non-mammalian cells. Some can even have multiple flagella. And tomorrow we're going to get started with a tour of the cell.
Can you go back to flagella real quick?
Sure. Tomorrow we're going to get started with all of the organs of the cell. So go ahead. I want you to, as homework, watch the video linked to my website called Tour of the Cell. It's gonna go through, I think there's 2 videos, one on the cytoskeleton and one on the organelles. Watch those in preparation, and tomorrow we're gonna glide through all of the organelles. A lot of them are ones you've heard of before, if you've ever taken even the most basic biology class.
Watch Tour of the Cell, what was the other one?
I think there's 2 linked. If you look at where the chapter 3 PowerPoint is on the Moodle, there should be 2 links right underneath.
So it's safe to assume that the class is gonna be on Wednesday?
I don't know, probably not Wednesday, because I don't want to rush getting through everything tomorrow.
Okay,
So at the very earliest, it would be Thursday.
okay.